Hello everybody, so now we're going to introduce the terms for chapter 15. And this is another chapter that's going to be important for respiratory majors. So first term we've seen before, that's going to be pressure. Variable is going to be a capital P. One unit is pascals, but it can also be pounds per square inch. But we're actually going to stick with pascals when we plug in our formulas. The other term is temperature. That's going to be capital T, and we're going to use a standard temperature scale. That's going to be in kelvins. And the next term is going to be volume. In volume, I use a capital curly V, and that's going to be in cubic meters. So the equations that we're going to need for this chapter are from before. Temperature in kelvins is 273.15 plus the temperature in Celsius. And this formula here, which is pretty general, initial pressure times initial volume divided by initial temperature in kelvins is going to equal final pressure times final volume divided by final temperature in kelvins. And we're also going to introduce this term here. If they ever say standard temperature, that means I'm going to define this to be T0, and that's just going to be 273.15 kelvins. And if they say standard pressure, we're going to define it to be atmospheric pressure, or 1.01 times 10 to the 5 pascals. So this is just an introduction to the terms that we're going to cover for the lecture for chapter 15. So this is going to be our lecture for chapter 15. So before we start with the lecture, let's look at a simulation. So you have a chamber here. You can change the size of the chamber, change the volume. Here, this is going to measure pressure. We're going to keep that in pascals. And this is going to be the thermometer. We'll keep that in kelvins. So there's going to be three basic terms there: pressure, temperature, and volume. So let's add some gas to this chamber. So let's see the things that interplay. If you increase make the volume smaller, you notice the temperature rises and the pressure rises. And if you make the volume bigger, the temperature drops and the pressure drops. So that's going to be the first equation that we're going to look at. Okay, so let's just simplify. Let's say that you have a piston. It's pretty much a tube with a movable lid. And let's say that the lid starts off down here. So initially this thing is going to be cold. So it's going to have some initial temperature, which is going to be cold, which means that the gas atoms are moving slowly, so they can't travel very far. So they can't really push that hard on that lid, so it's going to stay a small volume. So this is going to have some initial volume, and I'll try to fit it in here, V initial. And this gas is going to exert a pressure on the lid here, so it's going to have some initial pressure, P initial. Now let's say that you have that same piston, but now you're going to place it under high heat, so a big flame here. So the temperature is going to be high. So what's going to happen is that the gas atoms, they're going to be able to move around really fast, and they're going to hit the lid with a lot of force. And because of that, they're going to push the lid up higher here. Because the gas atoms, as they're moving fast, are just hitting the lid harder and harder to make it rise up. So it's going to have, in this case, a high temperature. The volume is going to be bigger. Oh, excuse me, this should be final temperature. So that in this case here, the final volume is going to be different. It's going to have a bigger final volume. And also the pressure here is going to be different because you're going to feel the lid pressing upwards on you. So we can relate all those terms. And we're just going to say that in general, the initial pressure times the initial volume divided by the initial temperature is going to equal the final pressure times the final volume divided by the final temperature. But in both cases here, the temperature needs to be converted into kelvins. So next, let's go back to the computer simulation, and we're going to look at this is a pretty big equation, so we're going to make some simplifications here to this equation. So here, let's say that I keep the pressure the same. So what that means is that I'm just going to open up the lid so that the gas is in contact with the air outside, so everything gets equalized, so the pressure is constant. So if you keep the pressure constant and if you add heat, then what's going to happen is that all the gas is eventually going to leave the chamber. So that means that it's going to take up more and more space on the outside. So if pressure is constant, if you increase temperature, volume should increase. So the equation in this case here, it's the same formula, but now we're going to assume that the pressure is going to be constant. So a specific application of this one is if the pressure is constant, they're just going to cancel out of this equation here, and you're going to be left with this formula. So in a case where you have a constant pressure, this is going to be initial volume divided by initial temperature in kelvins is going to equal final volume divided by final temperature in kelvins. So the next case that we're going to look at is going to be constant temperature. So this one I can't really, the computer simulation doesn't really work for that one. So let's just assume that you start off with the same formula. Initial pressure times initial volume divided by initial temperature is going to equal final pressure times final volume divided by final temperature. So let's say that you have a car engine, a piston in a car engine, and you're able to set it up so that the engine, this piston moves up and down, but you're able to add and remove heat so that you keep the temperature the same. So you keep the temperature constant. So in this case here, what's going to be the same before and after the piston moves up and down is going to be the temperature. So it's going to cancel on both sides. So in this case here, if you have an ideal gas where the temperature is constant, the above formula simplifies to initial pressure times initial volume is going to equal final pressure times final volume. And in these problems, sometimes they'll give you some terms, but not explicitly. So if they mention standard temperature and pressure, or STP, that means that the temperature is going to be 273.15 kelvins, and the pressure is going to equal 1 atmosphere, or 1.01 times 10 to the 5 pascals. Something else for these work problems is that let's say that you have your piston here, and let's say that the piston starts off with the lid here like this. So this is going to have some initial volume, and you'll be given something like this, where they say that the volume doubles or triples or halves. So you can use this to make the calculations a bit simpler. So this is going to be initial volume. The final volume is going to be twice that. So the lid rises up to here. So if they say doubles, what you can do is just set the initial volume to 1 and set the final volume to 2. If they say halves, just make the final volume 1/2. So this completes the lecture. This simulation is going to help us to understand how pressure, temperature, and volume are related. So we have two different cases here. So in the case on the right, you have a gas tank, so the volume here doesn't change. And then you have, let's say, air inside this gas tank. And on the left, what you have is a piston. So what that is you have a cup, and then you have a movable lid. And inside that movable, so inside this cup with the movable lid, you have gas atoms again here. So here, the lid can move up and down. And so what's going to stay this, well, we'll worry about that in a little bit, but let's concentrate on first is look at those gas atoms. So in both of those cases, inside the gas tank and inside this piston, they're on average both moving at the same rate. What that means that in both cases here, the gas atoms are at the same temperature. So let's increase the temperature for both of them. So if you notice, as you increase the temperature, the gas atoms move faster. And as you lower the temperature, the gas atoms move slower. So that's going to be the first case. So just the rate of motion, that's going to represent the temperature of the gas atoms inside those two different kinds of containers. So now let's concentrate on the container on the right. So here, the container on the right, its volume is going to stay the same as we increase the temperature. So let's see what happens to the pressure in this case. So you can ignore the one on the left for now, just concentrate on the one on the right. So as we increase the temperature, you notice that the volume remains the same. The volume stays at 1, but the pressure increases. It goes from 0.4 to whatever the given units are to 2. So the pressure increases. And the reason why the pressure increases is because you keep the volume constant, and those gas atoms, because they're moving faster, they're exerting, they hit the wall with more force, and that force is spread out over that area, which means that the pressure is going to increase. So that's the first case. If you keep the volume of a gas constant, then as you increase the temperature, the pressure has to increase. So that's the first case. If the volume is constant and you increase the temperature, pressure is going to increase. And also, if you keep the volume constant and you decrease the temperature, then that means that pressure is going to decrease. So that's the first case. Now let's concentrate on the one on the left. So on the one on the left, this is a piston. So what's happening inside the piston is that because the lid can move up and down, what's pressing the lid down is the air above it. And the air above it, that's going to remain at air pressure. Or what that means is that the pressure on this piston is going to remain constant. So you'll notice that the pressure is going to remain at 1 here. So in the case of a piston, where you have if the pressure remains constant, let's see what happens in this case. If you increase the temperature, that means that the gas atoms are impacting this piston with more force, and they're able to push the piston upwards. And what that means then is that the volume of this piston is going to increase. So the other case is that if you have a gas and you keep the pressure constant, then when you increase the temperature, that means that the volume is going to increase. And vice versa, if you keep the pressure of a gas constant and you decrease the temperature, then that means that the volume is going to increase. So these are two separate relations, but you can combine them both into one equation that we'll be looking at. But again, the idea is that if you keep the volume constant, you increase the temperature, then that means that the pressure is going to increase. And on the left, if you keep the pressure constant and you increase the temperature, then that means that the volume is going to increase.